Welcome to all. I am Dr.D.HEMANAND, professor from the CSC department. I'm going to discuss about computer organization and architecture with question and answer. So now we are going to go through the syllabus of computer organization and architecture regarding GATE syllabus. Here we are having machine instructions and addressing modes, ALU, data path control unit, instruction pipelining, pipeline hazards, memory hierarchy, cache, main memory, and secondary storage, I/O interface. This is the overall syllabus of computer organization and architecture. Now, today we are going to discuss about machine instructions and addressing modes. So, this is the topic-wise weightage analysis of GATE from the year 2008 to 2023. Here, machine instruction and addressing mode, ALU and control unit, instruction pipelining, memory hierarchy, and I/O interface. When go to this analysis, we can have more number of questions in the topics memory hierarchy and also in the machine instruction and addressing modes. In recent years, we are having more number of questions in this particular machine instruction and addressing mode and also in the memory hierarchy. So almost no other topics involved in the last few recent years. So first, we are going to discuss about what is machine instruction and what is about addressing modes. Machine instructions is nothing but it is an instruction that is tells from CPU to how to execute the instruction. Okay, that is CPU is instructed to perform a specific operation using the group of bits. This is called the binary instruction coding. The operation code is associated with each instructions, which identifies the overall purpose of the types of the machine instruction. The instruction sets a group of machine language. This commands for a CPU, the subset of instructions designed to enhance the performance of the machine depending on the situation. The CPU follows an instruction cycle from boot up until the computer has shut down. That is known as the fetch, decode, execute cycle. So there are three different types of machine instruction type. So based on the type of data transfer, here we can have the data transfer instruction. So the transfer instructions allows data to be transferred from one place to the another without altering the content. The short transfer may occur between the memory and processor register or between the processor register and the input output. So here some of the instructions are there. For example, load, in, move, out, push, store, pop, exchange, etc. So load instruction transfers the transfer of data from memory into the register. In instruction that receives the data from an input device. Move that is used to data transfer between the registers. Out that is used to outputs data from the register. Push it used to push the data from the register towards the top of the stack. And store that is used to transfer the data from the register to the memory. Pop fixes the top data from register or stack memory. Exchange transfer information between the registers and memory. So next one is the instructions for data manipulation. This is another type of machine instruction. This used to used for data manipulation elements of machine instruction. Calculated by adding, subtracting, multiplying, dividing, incrementing, and decrementing. And then we are having logical and arithmetic instructions. So here the function performs arithmetic, shift left, arithmetic, shift left and arithmetic and shift right, etc. So nonsense and logical instruction type. So here bitwise operation like under, not exclusive of shift and rotate are performed. So next is instructions for program control. This is another type. So a program control instruction specifies a condition that affects the program counter. Okay, here the example is given. So branch, skip, call, test, etc. This is the corresponding mnemonic we are using in the instruction for program control. So next we are going to discuss about addressing modes. The addressing modes help us specify the way in which operands effective address is represented. So effective address is an exact memory location of the operand's value. So some addressing modes allow referring to a large range of areas efficiently, like some linear array of addresses along with a list of addresses. The addressing modes describes an efficient and flexible way to define complex effective addresses. So a set of linear instruction as operands and opcodes. An addressing mode has no relation with the opcode, and it basically focuses on presenting the address of the operand in the instructions. So this is one of the addressing mode called implied addressing mode. This type of addressing mode is also known as the implicit addressing mode. So we can provide the operand implicitly. Okay, without giving directly, we are providing the operand value implicitly. The implied addressing mode does not specify an effective address explicitly. Okay, here is one of the example of implied addressing mode, the opcode and the address. The address is directly stored here. Okay, this is the example mode AL, 35. So the mode data of the particular data into the register. So next is immediate addressing mode. In the case of the immediate addressing mode, the operand's value is mentioned explicitly in the instruction. Thus, we don't require the effective address as operand is defined explicitly in the instruction. So this is one example, add R2, 100. 100 is the value. Okay, this symbol is followed by the number. Okay, that is represents the value. So store R2, 100H. Here the add instruction will add 100. The number numerical value 100 to R2, register R2 content. And this ampersand sign present in front of the value to indicate the immediate value that is to be operated. So register addressing mode, all the instructions include operands. These operands could be a processor register, a memory location, or an IO device. Here the instruction that use the processor's register to represent the operands refer to the instructions that are in the register addressing mode. So the effective address here refers to the register in which the value of the operand is present. Here effective address is the register. So to represent the register addressing mode, here are the two instructions. We can see example add x4, x3, load x3, x2. Okay, here are some of the examples for register addressing mode. Direct addressing mode. The other name for the direct addressing mode is the absolute addressing mode. In this case, the instruction possesses the address of the actual location in the memory, whatever the value of the given operand is stored. If here the effective address is the any memory location refers to the effective address. For instance, we can see the example add R2, A, store R2, B. So here we are going to see about the GATE 2024 question. In this particular topic, the processor with 16 general purpose registers uses a 32-bit instruction format. The instruction format consists of an opcode field, addressing field, two register operand fields, and a 16-bit scalar field. If 8 addressing modes are to be separated, the maximum number of unique opcodes possible for every addressing mode is. Okay, this is the question. The options are 16, 32, 64, and 36. So here we are going to see about how to solve this question. First, we need to write down what are the given what are the available data in the question. Okay, instruction size is given. So that is 32 bits. Instruction size is given in the question, and then given that number of registers is 16. Number of registers available is 16. So the number of bits needed to specify the register in the instruction is 4. Okay, instruction size is given in the question 32 bits. Given that the number of register is 16, so the number of bits needed to specify the register in the instruction is 4. Given that the number of addressing modes, that is also given in the question, that is 8. So the number of bits needed to specify the addressing mode in the instruction will be 3. So number of bits available for output, this is a formula. So from this formula, we can able to derive the answer for this question. The number of bits available for output, instruction size, addressing mode, field size plus 2 into register field size and scalar field size. So this is a formula to calculate the number of bits available for output. So the instruction size is given in the question, that is 32, and the instruction size is 3, and another thing is register field size, that is 4 and 16. Okay, all the data is now available here. So 32 minus 5, 27, 5. Okay, so the maximum number of unique output possible is 2 to the power of 5, that is 32. Okay, this is the answer for this question. So next question, this is asked in the year 2024. The processor, first to read the question, the processor uses a 32-bit instruction format and supports byte address in the memory access. The ISA of the processor has 150 distinct instructions. The instructions are equally divided into 2 types, namely R type and I type. And then whose formats are shown below. The formats are also given, R type instruction format and I type instruction format. In the octet, 1 bit is used to distinguish between the I type and R type instructions, and the remaining bits indicate the operation. The processor has 50 architectural registers, and all register fields in the instructions are of equal size. So let X be the number of bits used to encode the unused field, Y be the number of bits used to encode the output field, and Z be the number of bits used to encode the immediate value or address field. So we need to calculate this value, X plus 2Y plus Z. So we need to identify the values of X, Y, Z. So here the solution. So here the output field, we need to identify so value for X, Y and Z. So output, Y is the output field. There are 150 instructions. Okay. So and they are equally divided into 2 types. Therefore, there are 75 I type and 75 R type. 75 immediate type or 75 register type instructions. Since 1 bit is used to distinguish between the instruction types, the number of bits used to encode the output field is 1 plus 7, that is 8. The register field, there are 50 architectural registers, and all the register fields in the instruction are of equal size. So therefore, the number of bits used to encode register field is 6. So next, the X value, the number of bits used to encode the unused field in the R type instruction, that is 32 minus 8 is the output value, and these are the 3 registers of them. So 3 into 6, 18. Okay, 6 plus 6 plus 6. Okay, 8 plus 6 plus 6 plus 6. Okay, that is 24, 26. Okay, 26 minus 32, we will have 6. Okay, immediate value address field. Okay, that is the number of bits used to encode the immediate value divided by, or the address field in the I type instruction. That is 32 minus 8 plus 6 plus 6. So the 6 plus 6 is this is the register. This is for each register, 2 registers. So 6 plus 6 and then 8. So we will have 8 plus 6, 14, 14 plus 6, 20. So 32 minus 20, that is 12. Therefore, the values of X, Y and Z are 6, 8, 12 bits respectively. So the answer will be 6 plus 2 plus 8, 6 plus 2 into 8 plus 12. So that will be, the answer will be 24. So next question. This is asked in the year 2022. First, read out the question. The processor X1 operating at 2 GHz as a standard 5-stage RISC instruction pipeline having the base CPI or one without any pipeline hazards for a given program P that has 30% branch restrictions, control hazards incur 2 cycles stall for each branch. A new version of the processor H2 operating at the same clock frequency as an additional branch predictor unit that completely eliminates stalls for correctly predicted branches. There is neither any savings nor any additional stalls for wrong prediction. There are no structural hazards and data hazards for X1 and X2. If the DPU has a prediction accuracy of 80%, the speed up obtained by X2 over X1 in executing P. So that is the question. The options are also given here. So we need to find the solution for this question. First, we need to identify the data available in the question. The X1 frequency is given in the question and X2 frequency is given. So that is 2 GHz and X2 frequency is also 2 GHz. The CPI is 1 is given in the question. The 30% of the branch, okay, that means having the stars of 2 stars and the BPU, if success, no stars, otherwise 2 stars. So the 80% prediction accuracy. Okay, these are all the given data in our question. So now we are going to solve this question. So speed up, we need to identify the speed up. So for that, first we can calculate with the help of the time. Okay, execution time. So execution time can be calculated by number of instructions into clock per instruction into clock cycle time. So speed up can be calculated with the help of this execution time. First we need to calculate the execution time and then we can find the speed up. The speed up can be calculated by old system execution time divided by new system execution time. So when number of instruction and clock cycles times are same, then speed up will be old system CPI divided by new system CPI. So normal processor CPI, if the normal processor CPI is 1 without any pipeline offset. Okay, normal processor CPI is 1 without any pipeline assaults. So given that the question program has 30% branch instructions, where each instruction will lead to 2 stall cycles. So the processor X1 has no PPU, therefore CPI equal to 1 plus 0.3, that is 30% of instruction. Okay, that is the branch instructions penalty, that is divided into 2, that is equal to 1.60. Okay, processor H2 has BPU, therefore CPI will be calculated as like this. So this is 30%, given in the question 30% branch instruction, where each instruction will lead to 2 stars. Here. So next 0.3 into 0.80 into 0. The BPU correctly predicted here. And then 0.2 into 2. The BPU wrongly predicted. So this is 80%, this is 20%. Next, speed up can be calculated by old system CPI divided by new system CPI. So 1.60 divided by 1.12, that is 1.4385. So the answer is 1.43. Okay, so this will be 2 decimal points. So we convert into 2 decimal points. So the answer will be 1.43. 1.43 will be the correct answer. So this is asked in the GATE 2021. Assume a 2-level inclusive catching hierarchy L1 and L2. That L2 is the larger of the two. Consider the following statements. S1, read misses in a write through L1 catching do not result in write backs of battery lines to the L2. S2, write allocate policy must be used in conjunction with the write through catchy, and no write allocate policy is used with write back catchy. So which of the following statement is correct? So there are 4 statements given here. We need to find out which one is the correct one. So based upon the statement given here, so here S1 read miss. So with the help of the statements given in the question, we can come into conclusion that correct answer is the option A. Okay, read miss in the right through L1 catchy recursive read allocate, no write back is done here. As in here, write through L1 catchy, both L1 and L2 are updated during the write operation. So during the read list, it simply bring in the list block from L2 to L1. So it reads one block in L1, okay, and then so S1 is the true statement. Next S2, this statement is false. Both the write through and write back policies can use either of these write list policies, but usually they are paired in this way. Okay, so this is considered to be the false statement. So the correct answer will be A. S1 is true, S1 is true, and S2 is false. This is the correct and correct option. So next, this question is asked in the year 2018. The question is, as instruction pipeline of the RISC processor has the following stages: instruction fetch, instruction decode, operand fetch, perform operation, and write back. So these IO, ID, OF, and WB stages take one clock cycle each for every instruction. Consider a sequence of 100 instructions. In the previous stage, for the instruction can take 3 clock cycles each. 35 instructions take 2 clock cycles each, and the remaining 25 instructions take 1 clock cycle each. Assume that there are no data assets and control assets. So the number of clock cycles required for completion of execution of the sequence of instruction is the 4 options given: 219, 104, 115, 220. So we can solve this question. Okay, here total instruction given the question is 100. The number of stages is 5. Well, in normal case, total cycles will be 104 cycles. That is 100 plus 5 minus 1, that is 104 cycles. For PO stage, 40 instruction take 3 cycles, 35 take 2 cycles, and rest of the 25 take 4 cycles. So that means all other stages are perfectly fine working with CPI. That is clock cycles per instructions. That is 1. PO stage, 40 instruction take 3 cycles, 35 instructions can take 2 cycles, 25 instructions take 2 cycles. Okay, that is this instruction is suffering from the stalls 2, 1, 0 respectively. So extra cycle would be 40 into 2 plus 35 into 1 plus 25 into 0. That is 80 plus 35, 115 is the correct answer. So 115 is the option C is the correct answer for this question. 115 is the correct answer for this question. So this is a question asked in the year 2018. The following are some events that occur after a device controller issues an interrupt while process L is under execution. So here 4 statements are there. Then the P, Q, R, S, T. Okay, which of the following is the correct order? We need to find out which one is the correct order. So P is the processor pushes the process status of L onto the control stack. Okay, that is which one is comes to the. We need to identify the order. Okay, first one is not come first. Okay, this is the Q will be the first thing that can happen at first, and then followed by this one. This is the second thing can happen, and then the processor loads a new PC value based on the interrupt. Okay, this is the third thing, and then processor executes the interrupt service routine. This is the next one. So last one is processor pops the process status of L. So this is the next step. This is the correct order. Okay, we can see the simple interrupt processing. Okay, we can, with the help of this diagram, we can understand, okay, which process will take the the order in which the process can occur. Okay, the device controller order system hardware issues an interrupt. Next, processor finishes the execution of the current instruction. Next, processor signals acknowledgement of interrupt, and then processor pushes the PSW and PC onto control stack. Processor loads a new PC value based on interrupt, and then save remainder of the process state information, process interrupt, and restore the process state information, and restores the old PSW and PC. So when you look on this, you can easily identify that the QPTRS. So this is the correct option. Okay. Thank you. Continue on next session.